Good morning, everybody. It's great to have so many of you being able to join here in person today. I want to ask you first of all, how many of you have actually driven in a truck like this? Nobody? Couple? In a car? Okay, many more. Maybe not in a car like this. It's a bit older than your time. So I'm going to talk about this a tiny bit now in the introduction. But first, my name is Iñigo Alonso Fernandez. Most of you know me. And I research in the product development area here in Chalmers. So let's talk a tiny bit about this legendary car. At the beginning of last century, the world was in the middle of a technological revolution, and cars were a big part of it. In 1909, the Ford Model T was released, and Henry Ford shared this vision with his management team. Not much room for choice here. Any customer can have any car painted any color that he wants, so long as it's black. Well, his vision might be, or was, that the Model T was to be the car that any person could or would ever need. So not too big, not too small, powerful enough, comfortable enough, and affordable to everybody. Why so little room for choice? Because what came out of this second industrial revolution, or Industry 2.0, which I don't think they called it like that back then, was this concept of mass production, interchangeable parts, the assembly line. What they did was make it possible to develop affordable products, so long as you were always doing the same thing over and over again. But, well, we are all different, and we have different needs and expectations and tastes, and one size does not generally fit all. And, you know, did people really only want black cars? Well, maybe Instagram was in black and white back then, and maybe they were fine with that. And again, not old enough to know that. And the reality is that the Model T at the beginning was not even sold in black. You could get it in red, gray, or green. And a couple of years later, they introduced this midnight blue. And it wasn't until 1914 that the black actually took over and was the only choice you got. But the vision of Henry Ford was never to have one single identical car to sell to all consumers. The Model T was a product platform. Different bodies could be attached to the common base, creating different variants that met the needs of different consumers. And over time, new options were developed on this base. But other companies were also part of the market, and they were developing new models that introduced new technologies and new features into their cars. And in 1927, at that time, Ford was only producing 4 Model Ts. That's the only type of cars they produced. And in 1927, they closed the lines down and production stopped. In theory, they were doing this because they wanted to retrofit the factories to release a new model. But actually, they hadn't designed that model yet. They had to spend some months doing the design and then retrofitting the factories and so on. They almost lost a whole year of production and sales. Meanwhile, some competitors like GM with their cheap Chevrolets ate their market share. That's not a great position to be in if you are trying to sell a product. And what this does is highlight the trade-off that you need to make when working with platforms between having flexibility in the platform to introduce these new technologies as they become available, and the value you get from actually reusing parts, because let's not forget, they were doing pretty well by being able to release very cheap cars because of the cost they made in the production. Coming back to the present a little bit, on the one hand, having to deal with many different components and production methods, paint colors, it's still expensive. So we still want to minimize that that part. But on the other hand, as we said, we need to meet the needs of many very different customers. So there is some trade-off to be made there. And the goal of my research is to find ways of designing platforms that are flexible enough to adopt these technologies changes as they come. Just some quick definitions, because I'm going to be talking about some things during the presentation, and I want to make sure we're on the same page. Well, when I talk about products, it's a thing that we have designed to fulfill some needs. Product platform, I use this broad definition of a collection of assets of different kinds that are shared by a set of products. In general, I'm going to talk about platforms that are done in purpose. So there is a platform strategy at the company, not just it happens by happenstance. When I talk about architecture, I mean the description of the structure and organization of the parts of the product. And then architectural constraints are the limitations that this structure places on the product variants that can be derived from the product platform. So one example that I will be talking about during the presentation is this head-up display, which is a component that lays there in the front of the car, in front of the driver, and is used to present some additional information to the driver of a car or any other vehicle. This is an interesting case because it's in a tight spot. There is a lot of geometrical constraints for it, and also has a wide variety of other interfaces from electrical data, optical with the windshield, and so on. So it's a multi-technological component that is more interesting to study than something more simple. And the question is, if we want to assess how valuable it is to introduce a new type of technology for this component over time in a platform that we might already have or are developing or thinking of developing. What we do nowadays might be gather a bunch of experts on the different fields involved and try to assess more or less, is this compatible or completely incompatible, or there's going to be some effort needed to adapt our platform to this type of technology. And this is challenging for several reasons. One of them, obviously, is once we go through certain path, we're making some architectural decisions that are going to be hard to change later, and they are going to constrain what we can do in the future with the platform. And on the other hand, the market and the conditions are always dynamic, are going to be changing, and we don't know which way they are going to change in detail, at least. And further, it's a tricky thing because you need to get a bunch of different stakeholders, both internal and external, to agree on what is valuable to base your platform on. So one of the questions is how do we decide when in the life cycle of the platform to invest in this flexibility, and how much do we need to do it at each step? So first thing we might do to try to answer questions like this is, okay, let's go to the literature, see what's out there, other people that have studied these problems, what are they proposing. So after looking at what's available, or at least a subset of it, my finding or my understanding is that the theories that are out there right now do not deal with the changes at the platform level. Well, in some cases they do, but when they do not focus on addressing what are specifics about the new technologies, or they fail to include several steps into the future with added uncertainty, or in the marketing cases, when they are defining product families, they might sidestep all engineering design issues altogether. So there's a lot has been written about this in the last decades. Just name dropping some of the things that are related to this. I'll come back to some of them later. But within these fields of study of product platforms and platform flexibility, there has been quite a bit written about it. But still, there is some parts that are not clear-cut and not easy to apply into the practice. So what is the problem in practice in industry now? Is that first of all, the pace of technology change is accelerating. It's not only going faster, but there's a second derivative is going really, really fast. Also, there is issues regarding sustainability that can place additional constraints on products and by that on the platforms that are derived from. And lastly, think about the process, how these decisions are made nowadays. There is still a lot of decisions that are made by committee, always with of course, best intentions and best expertise available on hand, but these are sometimes not optimal decisions made. So, for example, I just plot here different Volvo Cars platforms from actually 1927, if you remember that date. There was an overlap of 6 weeks from when the start of Volvo first car production and the end of the Model T production. And if you see, there is a quite linear trend here over time of platforms tend to last, I don't know, about 10 years or so, and then it gets replaced by new ones. But if we look at, in this case, technologies that are introduced over time, I just plotted here technologies related to safety aspects. We see that the number of things that need to be integrated on each platform is skyrocketing. So this is tricky, and those are just for safety things, but there's many other trends on digitalization, electrification, autonomous driving, connected vehicles and so on. And this is coming and coming and coming. There is a lot of it. So introducing these new functionalities and technologies has its benefits, but complying with the platform has also some benefits on the basic level on cost. And the current way of working is based on these expert opinions, and you cannot really assess the impact with any with much level of confidence. So I'm going to talk now a little bit. What did I do to address this and try to come up with a better way of doing things? First of all, as I mentioned, there's a big phase of looking at what's out there, published and written about in the academic literature. Then I worked, as Sula mentioned earlier, with 2 companies on some case studies, like the head-up display I mentioned before. We did meet and discuss this and run some workshops about it. In parallel, I did a lot of stuff on the digital realm, trying to model and simulate and visualize things based on the case studies, obviously. And finally, the last step would be to pick up all these nuggets of insight that we get from the previous activities and synthesize this into a coherent proposal for a methodology. Just to put some numbers on this effort, there is a lot of papers that I went through. I don't claim to have read every word in all of them, but I have a big collection now. wrote some papers that are attached to the thesis. I did a bunch of interviews, participated in many meetings, ran half a dozen workshops, and in general interacted with dozens of people at these companies, and internally in a research group too. Being a bit more formal, the methodology for the research that I'm trying to follow is the famous DRM, with these 4 stages of research clarification: descriptive study 1, prescriptive study, and descriptive study 2. In my case, I'm actually doing all of them to different degrees, being more comprehensive in the central ones, and the descriptive study 2, which is what is left for the next year or 2 years. It's coming up. This research clarification that I started with led to 3 research questions that the thesis tries to answer. The first one is about what are the challenges that exist for designing these product platforms that are flexible to integrate these new technologies. Second one is about how can we make decisions about these trade-offs, and what methods and tools are needed or could be developed to address the support of these decisions. And lastly, how do we model and simulate the value of flexibility in product platforms? So it's not something we guess about, but actually can back up with some quantification of some kind. And as I said, I wrote some papers, and these are attached at the end of the thesis. And each of the papers tries to answer to a certain degree the different research questions. The first research question is mostly dealt with in the paper A. The second one, papers C and D, mostly a little bit on paper D. And the third research question is mostly on the second paper, and a little bit on all the others. I will use these symbols here on the top left on the upcoming slides, so you know the content of that slide, to what research question and paper it relates to. And just so to be comprehensive here, how do these research papers fit into the DRM methodology? The first one, as I said, is mostly about the research clarification and setting up the design study 1. The second paper combines findings from the design study 1 and the prescriptive study in proposing a methodology. The third paper makes another proposal. Sorry. For an alternative method in for the prescriptive study. And paper D kind of does some additional research clarification for the descriptive study too. So, well, how can then engineering teams best assess these changes to platforms? What am I proposing? I'm proposing this methodology for assessing flexible platform architectures subject to technological changes. You can see the details on the thesis if you want to read the small print. But basically has 4 main phases. Strategy definition, where we, using the value-driven design methodology, try to figure out what are the expectations and needs from the stakeholders. Then technology definition, getting information from technology roadmaps and so on. And also the alternative architectures that are to be considered. Then a phase of modeling these things from the inputs from the previous phase. And lastly, evaluating those models to be able to give the decision support at the end. About the modeling, it's kind of at the heart of this proposed methodology, and it has several parts. I will go through them briefly. First, there is a need of modeling the product architecture, kind of, as I said earlier, how the different parts and components relate to each other. Then for those components or modules, we need to model their engineering performance. For example, in the head-up display would be what field of view we get with a certain mirror size and so on. Then we need to try to figure out how likely it is that a combination of components with a certain performance is to fulfill the needs of the customer, so they actually want to buy it rather than what our competitors are proposing. But that obviously depends on the price that the product can have. So for that, we need to model the variable cost and the fixed cost of producing this product. So there is a bunch of different semi-independent modules that need to play with each other, and that we use later on to make simulations and visualizations. Talking briefly now about, for example, the first part of platform models. The idea is to have parametric platforms where we can change parameters of the platform to explore the design space for the platforms, not the products derived from them, for actually the platforms themselves. This example is just geometrical parameters, but as I said earlier, platforms defined as sets of assets could include also other type of assets in the parameters, like suppliers and knowledge or production processes. Yeah, then the other big part of the methodology is the flexibility assessment. How do we compare these platforms with one another in terms of their ability to adapt to changes later on, so we can derive new products with new technologies. And here, what we proposing is calculating this net present value numbers for each of these. This is a design derived from a platform. There's a bunch of them that we could think of deriving from it. And then we need to take out the ones that the platform constraints disallow or make it impossible. So if we do that, we can tell for a platform which possible designs of it are actually more valuable. We can do that for a future scenario too. So what happens later on when the circumstances change in the context, in the market, in the technology availability. And then for this platform, there might be other designs that are actually more valuable. And they might be different than the ones we had before. So it's important to know how can one design of the platform evolve into the future. What are the chances it gets the opportunity to go up in the value rank here. So we can do that for an example here from paper B. We do this for a platform in several scenarios over time, and considering designs based on different technologies. In this case, as a constraint for the plotting, I put the volume of the component itself. So we can see over time what designs give us better value. And if we do this for alternative platform configurations, we can get a nice picture of what is possible and what to choose from. Still, it's very hard here to say what to do, which platform to select. So the next step is trying to combine that information into a metric that puts a number, so to say, next to the platform and tells us how good it is in terms of flexibility. For that, I use the value-weighted filtered out degree metric adapted from Visito and Ross. We changed a couple of things regarding the calculation of the value, and it basically says for a given design in an S scenario, or going from one scenario to a next scenario, how many designs that are possible are actually more valuable than what we came from. So if we look at each of the designs from before, we give them a value of this metric, and some of them are have the option of evolving into a higher value design later on, and some of them have less chances of making that transition. Coming back to the example earlier, if we do those calculations for the designs we had for each of the platforms here, we can see that for platform A, there is very few designs that are actually compatible with the platform. Which I say that this is because the platform is over-constrained. It has shrunk the space too much, and that gives us very little choices. I mean, very little room to adapt to changes that we still don't know about. So we are going to be less able to deal with big swings on the parameters that are uncertain now. On the other hand, we have this another platform where there is a lot of designs are still available, but that means that this platform is under constraint, because a lot of what enables these designs to be available for the future is space reservations and other kinds of waste. So we are wasting money and resources now for possible futures to a degree that is a bit unbalanced. And lastly, this platform C we had here, it's actually delivering in average better chances for their designs to transition to better or more valuable designs later on. Yet is not wasting so many resources in the present. So we still get our good chance of adapting to whatever comes next, but we keep cost in the present relatively affordable. This still gets us in a place where we have many design alternatives for the platform. And this is because flexibility is about adapting the structure of the platform to the changes. So a change happens in requirements or in the environment or the demands from the market, and then we do a small change in the architecture to keep it viable. But what about if we want to have the architecture of the product platform absorb these changes without us having to modify the structure? Is there a way of doing that? Can we provide this kind of passive protection of the value of the platform? And for that, I propose this concept of resilient design objects, which are components that are added to the product structure to absorb change, so kind of interrupt the chain of change propagation. And this work by being placed in parts of the architecture where it's more likely that the change might happen. So we are proactive in placing them there. And this enables resilience of the product platform, meaning being able to absorb changes without needing to change its structure. And this can reduce risks and increase the sustainability of the platform, so you don't need to scrap parts or designs that are could still be useful. So I'll go through an example here on how to use these resilient design objects. Imagine there's a shaft that connects a gearbox and a motor, and it's sized for certain torque. So it's all good and nice. You have standard interfaces. Pretty nice situation. You can model this architecture with a enhanced function means tree like this, where the function of providing torque is fulfilled by this design solution of a shaft, well, transmission system with the part of the torque being fulfilled by a shaft, providing the torque by the motor, and doing the reduction by the gear. Modeling like this, we can add some constraints. For example, the motor that we choose as a maximum torque that it can provide, and the gear, it has some constraints on the temperature it can sustain and the misalignment it allows for it to still work. So what happens if new requirements or new circumstances in the world make it so there is, for example, a different torque needed, or there is some forces perpendicular to the shaft that might cause misalignment. In this case, we might need a different motor, so we put an alternative design for this function, so we can actually fulfill the new requirement. But this new motor might, for example, cause some unwanted function because it's more powerful, it generates more heat, and somehow that heat gets transferred to the gearbox and makes it not work anymore. And same thing with the load on the shaft. Maybe it's a very small load like this, but it generates too much misalignment for the gear to take. What we can do to avoid having to change the whole shaft and maybe redesign the interfaces and do a big mess with the architecture there, is to, from the beginning, having this resilient design object, in this case, yaw coupling. If you know, this is a way of uniting shaft with elastomer in the center, some kind of rubber. This would allow to kind of stop the propagation of these unwanted effects in this system. So just by placing an additional component, the architecture of the system as a whole is resilient against the changes in, for example, of changing a new motor, and the heat now is not a problem anymore, or having some small force that might cause disalignment. This component absorbs that change, and we can carry on with the same structure, same interfaces, and so on. So trying to wrap things up a little bit so I don't run out of time. Coming back to the research question, what challenges exist when trying to integrate these technologies? You can see the whole list on paper A, but the main challenges are that it's difficult to make these decisions based on information that, although might exist and be available, might not be easy to put together to compare and to make the trade-off. Then about the decisions, how to do this, I propose this methodology I talked about earlier, where a central part is this measurement of flexibility of the platforms. So how does that fit within the literature and the existing theories? Just as an example, a couple of the references I mentioned at the beginning. In some cases, when the literature talks about architecture modeling, it's very good at having all these tools about putting things together, doing modularization and so on. But in general, that part misses modeling of the uncertainty and the evolution of the platform through its life cycle. Other kind of literature exemplified here by these Ross ideas about trade spread exploration does take into account this uncertainty and looks into the future, and does a good job into connecting the fulfillment of the stakeholder needs to what's going to happen later on, but doesn't include much in the sense of engineering design. So there's little in terms of modeling of the performance of components and so on, and it's based more on ideas about change management in requirements and so on. So what I'm trying to do here is to have architectures that don't need that many big changes and that actually consider the engineering design into these decisions. So just main takeaways here. First of all, that using parametric platform architecture can support this trade-off analysis among flexibility and constraints in product platforms. Very useful tool to have. Then second takeaway, using a metric for flexibility of product platforms with regards of technology introduction can support the definition of the platforms to a balanced level of constraints, so you don't over or underdo it. And third, that using resilient design objects allows you to be proactive in the design of the platform, so some of the future changes do not affect these constraints of the platform. So what comes next? I'm going to continue the study of the production platforms, so these are better fledged into the model. Also planning on being a bit more explicit on the incorporation of impact of sustainability considerations in the methodology. And lastly, big chunk, it's going to come on the development of software tools implementing these methods, the whole methodology, and then trying to validate both the methodology and the tools in real case system industry. And with that, I just want to thank the Vinova, Volvo Cars, Volvo Trucks, who provided financing for the project BIS that I've been involved in. And I want to thank, of course, Massimo for being the main supervisor, and Ula, and from Volvo to the Cars, Thomas in person. Thank you very much. But there is a lot of people, both at Volvo Cars and Volvo Trucks, that have helped a lot. So thank you to all of you. You might be connected online. Timo, Andreas, Anup, everybody, thank you very much. It's been a pleasure so far, and I hope we can continue this a little bit longer. And with that, I'm done.